Hi, and welcome to StoneRose35's YouTube channel. In this video, I'm not gonna talk about design and software in general. There's not gonna be any sound demos, but I'm going to talk about electronics design, PCB design, schematics design, and so on. Why do I do this? Because building these devices required at some point to design specific PCBs. To get the full history of this, maybe just roll back a little bit. When I did my first experiment with a Raspberry Pi Pico as an audio effects or guitar effects processor, I quickly realized that I needed an additional PCB, at least to do the digital to analog converter. What I then bought one of these boards, and because they're quite cheap, they work well, and of course this is designed for a Raspberry Pi and not for a Raspberry Pi Pico, but I quickly figured out how this is gonna work, which pins I need to connect, and so on. But this is only the digital to analog converter part, and I found that it's difficult to find boards which have both ADC and DAC. One I actually found was this audio codec board Proto from Microelectronica, I think it's called. And this I used, but this used a little bit outdated codec, which was difficult to handle, and also I wanted to have a guitar input and not a microphone output, and also I wanted to wire it up directly and not to use these 3.5mm jack connectors. Since I was already a pretty proficient, let's say, schematic designer, I built an analog modular system mainly using perf board. I thought, okay, now it's the time to move on and also learn how to actually design PCBs, since there are many small batch manufacturers out now where you can send Gerber files and then you receive a small amount of PCBs back at a pretty low price. And since most of the components I use now are SMD, I had no other choice. So what did I do next? This is not a fully populated board. This is just one of the trials I still have on my desks. I designed this first codec board, which mainly included the more modern codec, a CS4270 or 71. I don't remember exactly. And there I added some suitable power supply, a guitar preamp, and of course connectors which I can solder, no 3.5mm jacks, but rather just solder points. And of course the first iteration had some stupid mistakes. I couldn't really use them without manually cutting traces and just make tiny connections, but I was still quite pleased, so I decided to do a version 2 of this codec board, and this worked more or less flawlessly. I built a few of these codec boards, and I even sold a few of these. I even built a little test bench to just when I assembled them. I didn't buy the board fully assembled. I assembled them myself because I just like soldering, and I think I'm pretty good at it. So, and then came the next step, because this was part of devices like this, like a small input output with these 3 knobs and display and so on. So just minimal audio effects devices which are usable in a studio setup or maybe just as a little tool. But at some point I decided to convert it or to extend it into a full guitar, like a guitar stomp box, as you would like. I decided to build a full multi-effects device. This included, of course, stomp switches to change programs, abilities to save presets, and this one especially, this has some quite unique features which I designed for myself as a harmonica player. It has guitar input, microphone input, then some auxiliary input, headphone out, and stereo symmetric outs. So, and for this board, this requires the required a few more connections to make, or a few extensions, I built another PCB, which is this one, which I dubbed extension board, and this allowed to connect the foot switches and to have all the symmetric ins and outs and so on, and also a little EEPROM to save presets, and an additional microprocessor to handle the stomp switches and so on, to talk with the Raspberry Pi Pico. Yeah. And this, well, of course, also the first batch, I had some stupid mistakes on it, stupid PCB design mistakes, but also some general flaws. And well, so I thought at some point, maybe why not combine this board and this board into one, and also get rid of the major flaws this board has, and it has, so I could reuse some of the components, such as the power supply and so on. I have to build it only once. And yes, I worked on this for quite some time, always on and off, always when I had time, or when I was in the mood I did some PCB design, and when I wasn't, I didn't. So I think now is the time just to present this design, because there has already been some requests for boards. And a few days ago I heard over the internet that the Raspberry Pi Pico 2, or the RP2350, came out, and thought, okay, now it's really the time to present this board, because it's obviously gonna work with a Raspberry Pi Pico, and once the software is ready, also with a Raspberry Pi Pico 2, and also with Electrosmith Daisy Seed board. So let's start with having a look at the schematic. I start at the center, so to say. This 40-pin connector then connects to either a Raspberry Pi Pico board or an Electrosmith Daisy Seed board. And around the center are also all the peripherals, or all the controls, which are directly connected to the microcontroller board, such as the 3 potentiometers here, the clipping LEDs here, enter and exit switch, the encoder, and the display. And I organized the schematic the following way. I made several sub-schematics, such as a UI controller, the analog part, codec, headphone amplifier, and so on. And what is central as well is the power supply, and there I made many changes from the first iteration of this full board. The first iteration worked with a 12-volt AC power supply coming from outside. This is then converted through a halfway rectifier into plus and minus 12 volt, which I thought is a good idea, since I was used to work with plus minus 12 volt when building this analog modular synthesizer, but it has proven that this wasn't really a good idea for this device, because there was still hum inside, and I needed to add really big capacitors to get rid of the noise somehow, but it still remains in some settings. So I changed this, and now it accepts 12 up to, let's say, 15 volts DC, not necessarily stabilized. This is then converted to 9 volts for the analog part, the preamplifiers, and then 5 volts for the headphone amplifier, which is also an analog device. And then we have a separate 5 volt digital power supply, which is then powered using a switching supply. And so to have also already in terms on the power domain, to have a clear separation between digital and analog. So let's move on to the next sub-schematic, which is the UI. I dubbed this UI controller, since this is the part which is necessary to handle the stomp switches, handle the additional LEDs, and also an EEPROM to store presets onto. So this is built around the Atmega 8. It's not the most powerful microprocessor, but it surely serves the purpose in just converting stomp button presses into messages, which are then sent over an I2C bus. And also the EEPROM, of course, uses I2C to store and load presets from. Well, there's not much to say about this. And let's move on to the analog part. The analog preamp shows different sections. Here we have the microphone preamplifier part, which is built around the NE5534 op amp or microphone preamp, which is a pretty common design in many pieces of audio equipment. There is nothing special about this. And then we have the output stages here. This is a stereo out, so we have 2 times the same circuit, and the symmetrization is done electronically and not using a transformer, because I'm quite confident with working with op-amp circuits. By the way, the op-amps are all TL074s or 72s. And well, the analog part relies on a virtual ground, which is created using input follower with a voltage divider. Well, this is a major change because the first iteration worked with fully symmetric input and output voltages. And well, of course, what I needed to add is the coupling and decoupling capacitors. The HiSet part is also built around the single operational amplifier, and it uses a special virtual ground which is not shared among the others. This is really I thought is a good idea, to really split the HiSet part from the rest, not to introduce any noise over the virtual ground. Then let's move on to the codec. This is the CS4270 stereo in, stereo out codec, and the wiring is done pretty much following what's proposed in the datasheet of this codec. One thing to note, I added an oscillator, so there is no need to generate specific clocks for the codec from the microprocessor. This allows greater flexibility when choosing clock speeds, frequencies. Everything else is pretty much standard. And then, last but not least, there's a headphone amplifier included, which is based on the LM4881 IC. Also, the wiring is pretty much as proposed in the data sheet, so not much to say about it. Let's move on to the PCB itself. One basic principle I applied, that I tried to physically split the analog and digital part. So analog is everything on the top part. Here you see the microphone input with one of the op amps, or the NA. This is the NE5534, and the other op amps built around the analog part. There it's all on top, it means below this virtual line we have here. By the way, also the CS4270 has the advantage of having all the analog connectors on one side and all the digital on the other, and so this made it pretty easy to design it like this, or at least not too difficult. And power supply is more or less on the left part, situated here. Digital power supply is at the bottom here, just to again try to separate it as much as possible. And another principle I applied is to have all the connectors on the outside of the board. Here you see this 40-pin connector, which then accept an adapter board to either connect to a Raspberry Pi Pico or Electrosmith Daisy Seed. Regarding layers, I thought for a long time whether I should try to build this board using just 2 layers or more. The advantage of 2 layers is that it's still debuggable, it's still correctable, but I found out that it's pretty difficult to build, and also I would need to split ground planes quite a bit, and I've heard or I've read that this might also cause problem, and one idea or one principle which should be followed is to have a ground plane which is more or less which doesn't have too much cuts. So I decided to build it using 3 layers. So on the front layer is just the main connector. I first of all tried to to put as many connections on the front part. Where this is not possible, where traces need to cross, I also switched to the back layer here, which has much fewer connections than the front layer, and one of the inner layers is then the ground plane. Well, that's about it regarding this board. So if maybe if there are some PCB gurus watching this, I'll encourage you. I would be very pleased if you leave comments. This can be actually more happy about critical comments, something which might be wrong, or might be because as a next step, of course, I order this board, try to populate them, test them, see if they work, and if someone spots a mistake before this happens, obviously it's better than afterwards. Let's maybe end this video with showing an artistic impression of this board. This, of course, comes in there. The 3D view of KiCad comes in really handy. So this is how it might look. I didn't find the model for all the parts, so of course the oscillator for the codec is also there, and also some bigger capacitor. And the connection, I probably don't put connections like these, but I solder the wires directly to the board. But this 40-pin connector is gonna look more or less like depicted here. Here's the back side, and obviously the inner layer is not really visible. So thank you for watching and leaving comments, and well, I just already talked about it, but the next step is going to be ordering boards, ordering parts, assembling 1 or 2 prototypes myself. Well, if the boards work, I certainly put up another video. By the way, you can find additional information in the links in the description. I put the link to GitHub and also my web space, which is now online since a few months, where you can find additional resources. Bye, and see you in the next video.